All right, so new type of statistical inference. So far what we have done is a one sample Z interval for P. And the goal of an interval, in this case, this specific interval, is to use P hat to estimate P. All right. Today we are going to learn about something called a significance test, your very first significance test. It is going to be called a one sample Z test for P. And for our one sample Z test, our goal is to decide if a claimed P is reasonable. Okay? So in other words, if I were to say, man, Miss Meister drinks seltzer water for at least 75% of the time she's teaching AP statistics, that would be I'm making a claim about how much LaCroix I drink. And I'm out, by the way, hence I had to go get real quick. That would be me making a claim, and then we would look at a sample to decide is that claim a reasonable claim. Is that very good? So, when we set up a test, the first part of every single test we're always going to set up is going to be to state our two hypotheses. When we say H0, that is our null hypothesis. HA is our alternative. Okay. We're going to define P the exact same way we did for intervals. P equals the true proportion, by the way, not the true number, not the true count, not the true value. It is the true proportion of the time something happens. Not that I have a reason for suggesting you guys might have misdefined P before. Okay? Also, you guys, P is always somewhere between 0 and 1. P cannot equal 1.96, nor can P hat. I wasn't talking about you, Ava, don't worry. Okay. We're going to state our procedure still. And all of this, if I talk about those 4 C's, all of this is my choose. And choose your procedure based off of the information that we have. Okay? Then we're also going to check. I got really good news. The conditions for a one sample Z test for P are random, normal, and independent. How we check one of those changes ever so slightly. Okay? Does anybody want to guess what we'll put in this box? Our calculations. The calculations that you are going to include in this box are different because we're not calculating an interval. We're going to run a test, and when we go through this logic of this test, it will make sense, but for right now, the calculations need to include P hat. You're going to tell me what we call a Z statistic. That is not the same thing as Z star, okay? Again, we'll talk about this as we get closer. And in fact, it ties very much into what Hayden said about, I need my sample more standard deviations away. That's what this Z statistic is the number of standard deviations away our sample is from what we would expect. Okay? And then you're going to calculate something called a p-value. And your p-value is a probability. Our last box, we are going to conclude. Our conclusions are going to start with since. Comparing two numbers, I'll explain. We have enough evidence, or we don't have enough evidence, depending on if we do have enough evidence or not, to reject our null hypothesis. Therefore, and then we'll make a further conclusion. All right, so if I were going to try to take this incidence with joy, for a couple of things that we could do here, okay? All right? We didn't do a full formal test, but I can kind of give you guys an idea of what we figured out with joy, okay? Our null hypothesis was that she was doing well, 50-50. Or our null hypothesis, she was just guessing. Our alternative was that she was doing better than just guessing. What was our p-hat? She was right 11 out of 12 times. Our conditions are not met for joy because we'll talk about that a little bit more in a second, okay? When I said p-value is a probability, what was the probability she got 11 out of 12 right by just guessing? Does anybody remember? Our p-hat was the 0.917. Our probability that she got 11 out of 12 right, value. Everybody good? And that was enough evidence to reject the null hypothesis. And we are able to say she can smell if someone has Parkinson's or not. Everybody good? That's the basic logic. If our sample is unlikely, we reject the null hypothesis and conclude the alternative. That's what this conclusion is trying to say. We have enough evidence. So let's go through how we find each of these things on any given context, not just with joy. All right, so the first thing you are going to do is write your hypotheses. Your null hypothesis will always be P equals, and then some proportion that I'm going to put a question mark for. Okay? We don't know what it is. It depends on the context, right? If we were testing Miss Meister drinks a LaCroix 75% of the afternoon she teaches AP Stats, my null hypothesis would be P equals 0.75. Everybody good? It's whatever that percentage, that claimed percentage is. Our alternative is going to be one of three things. P is greater than that question mark. P is less than that question mark. Or if we don't want to make a choice, we can say P is not equal to that question mark. There will never, ever, ever be an equal to anywhere in our alternative hypothesis. Now, a one-sided test is either P is less than the question mark or P is greater than the question mark. A two-sided test is P is not equal to whatever that question mark might be. Okay, that P is not equal to. The basic idea is what we're going to do is we're going to find the z-score of our actual sample. Where does our sample fit with what could happen? Okay, and if our alternative is not equal to, we're going to shape both sides of our z-score graph. And if our alternative is one-sided, we've showed that side or that side. That's what, hence one-sided, two-sided. Okay. Your conditions, random, normal, independent. Lovely. Random, we're going to look, is it given? Independent, we're still going to look for, is our sample size less than 10% of the respective population? Hopefully those feel really good. Now, the logic of our test, going back to joy, we got that p-value by assuming our null hypothesis was true. Is everybody good? Okay, so that means the p-hats will be normal when NP, N1 minus P is greater than or equal to 10. Yes? And when we were doing a confidence interval, we said, hey, our goal was to estimate what P is. We don't know what it is, so we put p-hat in its place. Okay? Now we're doing all of our calculations based on we have a hypothesized value for P. Because what are we doing? We're assuming that null hypothesis is true. My null hypothesis is that P is equal to some value. So now when we check our normal condition, instead of using P hat, we're using the P from the null hypothesis. When I say P sub 0 here, that is P null. Just like H0 is H null, the null hypothesis. Null meaning nothingness, 0. Everybody okay? All right. So, do you guys know that Turner does all of the New York Times apps every morning, right? And so for a long time, somewhere between the two of us, we have a spreadsheet that is comparing her times, my times, and Mr. Richards' times doing the mini. And we kept the data for about 8 to 10 weeks. Every single day, like we would do the crossword and Turner would keep it in a spreadsheet, which sounds like her, right? Definitely sounds like her. Okay? And so Turner says she can beat me at the New York Times crossword puzzle 75% of the time. She has not made this claim, but I like making fun of her hence. Everybody good? We're at about 50-50 now. For a while, she never beat me, but now we're at about 50-50. She's gotten much faster, or I've gotten slower. It's actually really hard to tell. Okay, so my null hypothesis in this case. So setting up the test is basically we're going to state our hypotheses and check our conditions. Okay? My null hypothesis is the claim, which is P equals 75% of the time. Like I said, P should always be in between 0 and 1. It is the proportion of the time. So we take percentage and turn them into decimals. Okay. Where P is equal to the true proportion of times Turner beats Meister. What's my alternative? My alternative is what I'm hoping to conclude at the end. So, is this convincing evidence that Mrs. Turner is overstating her ability? Is she saying that she's winning more frequently than she does? So we want evidence against her. Is everybody good? So we want to show what do we want to show about her winning percentage? That it is actually less than 75%. So everybody good on how I came up with that specific value or why I chose less than? And most of the time, you're going to see something along the lines of convincing evidence of. And the phrase convincing evidence is your clue that you are supposed to be doing a test instead of an interval. Okay? Also, when you're supposed to do an interval, it says construct and interpret a confidence interval. Okay. Everybody good so far? And so, if I have those hypotheses and that parameter, the appropriate test is a one-sample z-test. All right, let's go through our conditions. Are our conditions met? Let's start with the random. Is the random condition met? We were given random sample. Normal. For our normal condition, we're going to say 100 times, what are we assuming to be true? The 75%, the 0.75, yeah? So 100 times 0.75, and 100 times 1 minus that, are both greater than or equal to 10. And then lastly, are independent. And I genuinely do believe this to be true. 100 is less than 1,000 of the mini crossword puzzles both of us have done. Because we've been doing it for several years, more than 3 years, since we were teaching in the old building. Long time. How are we feeling so far? Okay. Next. Real quick, can we think through the p hats knowing what we know? The mean of my p hats would be, remember we assume that the null hypothesis is true. So the mean of my p hats would be 0.75. We can think through what is the standard deviation of my p hats if the null hypothesis is true. That would be the square root of 0.75 times 0.25 over 100. Okay, hold on. So this is a picture of our possible p hats, yeah? So if I go 1, 2, 3 in each direction and count by 4%, 4.5%, right? That's kind of, so this would be 0.79. This would be probably, I call it 4.5%. This would be 0.84, and so on in the other direction, yeah? Give or take. That's using that standard deviation, okay? And what is our sample, by the way? What is our p hat? 67 out of 100. So 0.67. That one I didn't do on purpose. You guys, that'd be like right about here, yeah? Is everybody good? And if I wanted to know how far over it is, I could even find the z-score of that particular sample. We could say, how weird is that? Where does our sample fit if the null hypothesis is true? That's really what that z-score is telling us. Where does my sample fit if the null hypothesis is true? Which is based off the p hats if the null hypothesis is true. So I'm going to take my sample value minus my null value divided by my standard deviation. Again, that z statistic is telling us where is our sample relative to what should happen if the null hypothesis is true. At negative 1.86, I would call it fairly low, right? Okay? And if it's low enough, we reject the null. And we say, hey, we shouldn't have been able to get this sample if the null hypothesis is true. And the sample is the only thing we know for sure. Okay? So what we do is, how low is low enough? Well, what we're going to do is calculate the p-value. The p-value is going to be calculated on could you get that sample if the null hypothesis is true. In other words, what is the probability you get that sample when the null hypothesis is true? And I've got a value, a p-value of 0.01. I'm sorry, 0.03. Everybody good so far? Now, so we've kind of been talking with normal distributions for a long time about kind of both of these graphs meaning the same thing, right? They're very, very similar to each other. This one's in the context numbers. This is in a standardized form. That would apply to any distribution no matter what, as long as it's normal, okay? So in reality, when we talk about what does my p-value mean, the p-value has a very specific interpretation. So I want to use this graph to talk through that specific interpretation, okay? We said that the mean of this graph was 0.75 because the whole idea is we base all of these on the null hypothesis is true. So if Turner beats Meister, (75% of the time), which is essentially what the null hypothesis is saying, okay? The probability we could get, you guys, what did we get? This was a probability of this, right? Why did we use 0.67? Because that's the observed sample, right? That was the observed sample value, okay? The probability that we get a sample with 67% or lower, because we shaded to the left, is 3%, 3.1%, 0.031. Okay, hold on. Were we convinced about joy? And what was convincing? That the observed, the actual, the only thing we know for true was unlikely to happen. Is everybody good? So if something is unlikely under an assumption, but it happens, that assumption is probably a pretty crummy assumption. Is everybody good? Like, that's the statistical rules, okay? So, would you guys call 3% unlikely? Yeah. 0.031 is low, a low p-value. And if I reject the null, we can conclude Turner is overstating her abilities. Because of the two of us, she's the arrogant one. That's not true at all. Okay. So the general rule of thumb is if our p-value is low, we reject the null hypothesis and conclude the alternative. Is everybody good? Now, I'm certain some of you right now are saying, in fact, I bet I can guess your question. Let me see if I can guess it. Whisper it to Sam real quick. All right. If your p-value is low, you're allowed to reject the null hypothesis. So is your question somewhere on the lines of, how low does my p-value need to be? I always get this question. It's weird. It's almost like I can anticipate it.
Was it the 0.05 that we keep for this?
Well, the answer is, it depends. Your rule of thumb, if I don't tell you, your rule of thumb is 5%. Okay? But in reality, what we do is we do something called a level of significance. Okay? That level of significance, how significant does my sample need to be? You guys, I interrupted some of your pre-cal class because you were talking about Greek letters, and Turner even asked me, do you do the alpha with the fishy? Am I right? So it was some of you guys? What period was that? Sixth period?
No, you did with period too.
Oh, we talked about it in 6. I guess you interrupted there, so.
Well, I have both second and sixth period planning, so that would make sense that I would interrupt a lot. Okay, so this is alpha. You guys, when the computer does it, it looks kind of more like this. Okay, it is the Greek A, lowercase alpha, okay? And alpha is what we call our significance level. Typical values for alpha include 0.01 or 0.05 or 0.10. Remember how I said typical confidence levels were 90%, 95%, and 99%? Are we seeing a connection between alpha and confidence levels? There is a connection, sorta. Sorta. Don't read too much into it. But sorta. Okay? So if your p-value is small, that would mean your p-value is less than alpha. You're rejecting the null hypothesis and concluding the alternative. If your p-value is greater than alpha, you fail to reject the null hypothesis and therefore fail to conclude the alternative. Everybody good? I am not anticipating that you have mastery of this process after doing this one example. We are going to be doing significance tests and confidence intervals for the rest of the quarter. Lots of them, lots of practice. You will get it down, I promise. Okay? Ooh. Let's do just, well, you guys, we're not going to do all of this. We're going to do the choose and check. Choose and check. That's all I want to do today. And then we will finish out the calculate and conclude tomorrow. Okay? According to the National Institute of Health, 16.2% of high school seniors have used some version of an e-cigarette in the past month. A vape, whatever. Okay? Jay wonders whether this national result holds true for his very large urban high school. For his AP Stats project, he takes a sample of 150 kids, and he gets responses from all 150, and 20 say that they have used an e-cigarette. Everybody good so far? So, tell me something. As you're looking at this, what is the first thing that you, like, in your gut you feel like you should do? Even before that, yes, for sure. But part of me just wants to know, well, what is 20 out of 150? Are you guys with me? 20 out of 150 is 13%. Are you guys comfortable with me saying that is at least some evidence that the null hypothesis is incorrect? Are we good with that idea? The null hypothesis looks like it could be incorrect. Okay? Great. Well, what is my null hypothesis then? P equals what?
16.2.
No. Because P has to be in between 0 and 1. P is 0.162. You got to turn that percentage to a decimal. What is our alternative? In this case, we're looking for strictly different from. So my alternative will be that P is not equal to 0.162. And not done. We're going to say that P is equal to the true proportion of students. What is my population in this case?
Seniors who have used an e-cigarette in the past.
Seniors where?
All high schoolers?
his sample was the kids from his school. And I think he said students though, right? So his is just going to be students because the sample was students from Jay's high school. So the population we're going to represent is students from Jay's high school.
So he's sampling something different than what the population.
I got it. It's fine. He wants to know, is all of his school different?
Okay.
Everybody good? With, and we've done everything but the actual choice. What procedure should we use? A one sample Z test for P.
Do we need to write them separate, or can we write one sample and test for each true proportion there?
Probably doesn't matter.
Would it not, like, for the proportion, do we have to write would it be the proportion of students at Jay's high school who used?
Oh, yeah, for sure. Who used e-cig of some kind, yeah, for sure. All right, random? You guys, do you guys remember what SRS stands for? Not a stratified random sample, a simple random sample. Okay, so if SRS is the same thing as saying random sample, is given SRS. And normal. 150 times
0.162.
the P from the null hypothesis, because remember our calculations. All right, so because those two numbers are greater than or equal to 10, what does that tell us? Our assumed P hats are approximately normal. On your quiz, I did not mark you wrong if you didn't make that statement on your test. I do want you to do so, okay? The whole idea is the reason we're doing that is to make sure the P hats, what we're comparing, like when we think through, we calculate that Z statistic, and what we're doing is we're trying to see where does our sample fit with what should happen, okay? We're doing that within a normal curve, so it needs to be normal. You need to mention normality in some point, okay? And you got to say what is normal. Remember, we're comparing our sample to one of many P hats. Independent. Large urban high schools have plenty of students. We're going to say it's reasonable to assume 150 is less than 10% of all students at J school. It would not be reasonable to assume that of Grandview Heights. It was very much reasonable to that he's going to a large high school. And we will jump into the calculations a little bit more tomorrow.